I didn't check for echoes yet. Oh, no echoes. Get that. Maybe soon. Okay. I expected it to sort of pick a brightness and stay there, but I can live with that. As long as it's not flashing like a disco, right? Good morning, class. Who brought me an apple? Nobody? What makes you think you're going to pass the class if you don't bring me an apple? Right? You're supposed to give the teacher an apple every day, especially on Monday morning. Have you do anything fun this weekend? Anybody? I sat in my office and worked all day Saturday. This class is fun. Good. All right, let's get busy. Here. Room control. Screen up. I know. Projector mute. That's the button I'm looking for. Okay. So today, since so it's scarce. Since everybody knows that they can watch us live. Nobody there yet. Since everybody knows that they can watch us live and that they can watch the video later, I'm guessing that's why nobody's here. But not nobody, right? All important people are here. I just thought it was kind of weird that there's 4 people and 3 people and 1 people. You're waiting for the rest of the group to show up, right? They usually here. Yeah. It is. Oh, good morning. Okay. So most of the groups expressed on the little survey we did in the beginning, most of the groups expressed on the little survey we did in the beginning that you mostly want to learn about how to do better at programming CNC machines, especially like mills and lathes and stuff like that. That was the biggest thing. Now, it was the person that didn't want the class to be about G-code, and neither do I, because that would be a boring class. And there was the person that didn't want the class to be about programming and stuff, which I think is kind of weird when it's a computer-aided manufacturing class. But I think I know what they mean too. Not sitting down in a classroom. Who's ever had the computer science class where the teacher writes the code on the board and expects you to write it down in your notebook? No, when I took computer science classes, they did that. And what's the language where there's like a semicolon at the end of every line? C does that, right? C and C++, I think you put a semicolon at the end of every line. If you copy down his code, or if you submit it, we had like written quizzes in computer science class, which was amazing. Because it was back in the day, it was like one computer. No, not quite that bad. But if you forgot one of those semicolons, you didn't get credit for doing the homework, right? You had to do, and there was a reason for that, right? It wasn't an accident. They weren't just being a jerk because they had the authority and they could be a jerk. It was that idea of attention to detail. And so today, what I want to do is I want to talk in detail in a whole stack of brand new whiteboard markers I was going to bring with me. A whole stack of them. I know. Yeah. Jordan. Hey, Joel, this is Toby. Hey, I was going to bring whiteboard markers with me so that I could actually use the whiteboard in the classroom where I'm teaching. Yeah, I didn't. I was wondering if you could, make sure they're good and working and new and more than one color. And you could send somebody with them too. It's Salisbury 407. Yeah, thanks. All right, great, bye. It's like DoorDash for markers.
So I don't know if someone already brought this up to you, but like a discrete licensing issue.
There's no discrete licensing issue.
So this weekend last night actually we had trouble.
There might have been a problem last night. I don't know.
Yeah. So
tell me what it says.
So there was no license available on the license server when you set up the information they tell you on the Canvas page or the hub page. So I opened a ticket and I just got an email this morning that said currently where there's an issue with our license for a screen, our administrators are looking into it. So I don't know if anyone here is able to run it, but at least I have an outstanding ticket where they say
they're not looking into it that strongly because they haven't called me yet. I know exactly what it is.
Cool.
We updated our license, but they have to actually push out the update to the license server.
Yep. Okay.
I'm certain that that's what it is. And it would have been January 30th because that's when the old license expired.
That makes sense.
But if I log into their support, I know for a fact that our license expires next January 30th now.
Well, I guess
so if they haven't reached out to me by the end of class, remind me and I'll go talk to them.
Sounds good.
Because all they have to do is delete a file and upload a new file to the server. I thought you were going to talk about a different problem, and that wasn't actually a problem. That was just a step. It's in the manual, so it's a feature, not a bug. Okay, where was I? So what I want to do today is I want to talk about no matter what CAM software you're using, the steps that every toolpath has in common, and how to and since you're the programmer people, how to decide what those steps are. So it doesn't matter to me what CAM software we're using. They all have to do the same thing because the toolpath itself has to have those things in it. That's what I want to talk about. Let's see if I can get anything going here. To do that, Lou, let's talk about very quickly the steps from concept to part, right? So here's a part. I have a part. Before I had the part, I had to have had an idea, right? So it had to be up here before I can get here. Once it's up here, what do I do very quickly? Just step me through the steps. You guys know, you've done this before, right? Everybody in the room has made something before, right? All right, so once I have the concept in my head, what do I have to do next? Yep.
Yeah, like a general sketch film.
We need a sketch. Right, and we'll call that the art. And that sketch could be just a sketch, right? It could be just a sketch on a napkin. It could be a solid model that you've done finite element analysis on. It's got tolerance drawings that have been printed out, right? That's the art. But you have to take the concept and make it into the art. How much detail does the art need to contain? But it could just be a sketch on a napkin. It could also be a solid model, detailed drawings, lists of specifications with bills of material and all that stuff. How much information does the art need to have? Needs to have enough information. Thanks. I did find one that worked. Thanks, Joel. It's a good workout, though. It needs to have enough information so the person making the part can make the part. Is that fair? So it doesn't often, especially here at WPI, when we're doing project work, the designer is the manufacturer. We've all seen it, right? And so when the designer is the manufacturer, you don't need to put as much detail on the drawings. Because, well, need to. It really depends on how quickly you want to make the part. Do you want to keep redesigning it every time you get to the step where you need to know the information? But so that's sort of personal choice. But we often see, especially at this level, we'll see art that is more like a sketch. And it's because you're designing it as you're making it. Okay? That's okay if the designer is the manufacturer, and if you're not going to have somebody else make it for you. If you're going to have somebody else make it for you, you're going to have better details, more information. All right, we've got to have the art. Once we have the art, we've got to come up with a process plan. We're going to say, how am I going to make it? So the art simply defines what I want to have. Once I've defined what I want to have, I'm going to decide how I want to make it. So we decide, do we want to use a milling machine? Do we want to use a lathe? Do we want to turn it? Do we want to mill it? Are we going to have a grinding process? Are we going to just 3D print it, send it off to Foisey? I mean, the building formerly known as Foisey. Are we going to outsource the manufacturing? We're going to send it to somebody that has a water jet and make it for us. We're going to ask the EDM group. Where's the EDM group? We're going to ask the EDM group to just make it for us. Once we decide that step, right? So we've got art, we've got a plan. We've got our plan. Then we're starting to get towards the detailed toolpath steps. And so I got some art for this piece a while back. And so the art defined the shape. It defined this. No, there's no bearings on this part. But often you'll have a hole that has a more specific tolerance because the part has to rotate around the bearing, right? So it's kind of a locational and a precision tolerance. The part didn't actually have any of those. But it had all these different holes in it. It had these little pockets in it. It's tilted in this direction like that. And so the first step I had to do when I wanted to understand how to make this part was I had to decide what's the stock material going to look like. What I could do is I could ask somebody to 3D print something that's just a little bit bigger than this, right? I could get a near net shape part and then do finished machining on it. Maybe it didn't have the holes in it, something like that. I choose a block of material, a billet of material. Once I've done that, I got to figure out how am I going to fixture it in the machine tool. So that plan is going to include what piece of material, not what material is it. The art defines the material. The designer has to pick what are you going to make it out of. But you, the manufacturer, need to pick which specific piece of material you're going to cut it out of. Right? So I pick a material. So I've got to have stock material. So this is stock material. I've got to have art. I've got to have a design that defines what the finished part looks like. And so we're talking about right now the whole part. But this is, it's kind of like a fractal. So, you know, a fractal, it looks like something that if you zoom in, it still looks like that. And when you zoom in some more, it still looks like that. And so it's kind of like a fractal in the sense that the steps that we have to do as you get to a finer and finer detail, they're still the same steps. So for the part, we need to have some description of the art. We need to know the material we're going to cut it out of. When we get to making a specific tool path, so we're making just, let's say there's a chamfer that goes on the outside from here around back to here. And so when we're planning that, just that one operation, there's one tool, it went around in a contouring operation like this, came back up. When I'm planning that, before I can plan it, I have to know what did the material look like just before that. So just before that, we've done a lot of the other operations, right? Just before that, I had to know what did the stock material look like just then. And I had to know what was the material that I was removing. Now, why did I need to know the material?
Margins and stuff, how fast.
Right, I need to know the bulk material properties so that I can figure out things like feed, speed, depth of cut. And with a milling operation like this, our depth of cut is two-dimensional, right? It's got an axial depth and radial depth. So it's how far down into the material you go, how far over do you step. Right, so every single tool path, whether it's figuring out the complex program for the whole part, or just that one chamfer, or just that one drilling operation. It has part. It has some finished part that it has to look like when it's done. It has some material that it's made out of, and that material has a shape. There's a particular specific shape that it looks like just before we do it. Then we can figure out our feed speed, depth of cut. Now, what else do we have to have? We said fixturing, we didn't write it down, right? So as soon as we apply this to our material, we have a cutting force, right? So as soon as we apply feed speed, depth of cut to our material, we have a cutting force that's trying to move the workpiece. So we have to have fixturing. Now, what's scary about fixturing? It's nice because it holds our part, right? What's scary about it?
Cut the vise.
Yeah, we might accidentally cut into it with our tool path if we're not careful when we do our feed speed depth of cut. So in this depth of cut in the CAM software, when we're putting that in, what are we typically entering? What are the CAM softwares typically call depth of cut in a milling operation? The tooling manufacturer will give you some ideas of what it should be also. What does the CAM software call it when we're inputting it? Yep.
Feed rate or something?
So feed rate is feed rate, and it's called feed rate. Yep. Anybody? So in a spree, it's usually incremental depth. And that's how far down are you coming for each pass as you go through the material. And step over. Any guess what step over is?
Step over X or Y.
How far are you going to move over at X and Y? Right. So not all CAM software will call it incremental depth and step over. But all CAM software will have a way that you can input this information. Because this is something that we as engineers have to pick. Now, speed. What are the units for speed? Surface feet per minute if we're here in America. In meters per minute if you're anywhere else in the world. But surface feet per minute. So what is surface feet per minute? It's how fast the cutting edge of the tool is moving through the workpiece. So it's the velocity of the cutting edge of the tool as it moves through the workpiece. On a lathe, if this was a turning operation, then this motion, so the workpiece is moving this way, tool's moving that way, it really doesn't matter. It's relative motion between the tool and the workpiece, right? And so if this is a turning operation, the rotation is like this in this picture. And the cutting edge of the tool is right here. It's pushing the workpiece into the tool. The chip comes off, right? So that's the speed that we care about in machining. Now, in this turning operation, we can figure out what the revolutions per minute need to be in order to give us a specific speed, right? We just need to know what the diameter is. And it's one circumference per revolution, so pi times diameter for each revolution. And we can go from RPM to SFM as long as we remember that 4 equals 12 divided by pi. You got to convert from inches to feet or feet to inches, depending on which direction you're going in this math, right? So that's our speed. And our feed is how fast we're moving, either in X, Y, or in Z when we're moving our tool relative to the workpiece. The cutting happens because of the rotation. Okay, so every toolpath has to have these things. This is the physics here that causes the cutting force. The fixturing has to be sufficient to withstand the cutting force, and it has to be out of the way, right? So we can't run into it with our cutting tool on accident. Sometimes it's okay to run into it with our cutting tool on purpose, but it's never okay to run into it with our cutting tool on accident. When you're doing it on purpose, especially if you're doing it here at WPI, please ask permission first. Don't just do it on purpose and say, like the Pee Wee Herman thing, I meant to do that, right? That's not what I mean by on purpose. All right, so we got to have our fixturing, and that's sort of the physics of everything that we have to have. But how about the mechanics of this? So in order to do this, what else do we need? What's missing besides we got our feet speeding up the cut? What's that apply to? It's applied to a tool, right? So I have to have a tool. You can't do it if you don't specify a tool, right? Who's used the CAM software and they tried to create an operation, but they forgot to tell the software which tool it was going to use? When you click OK, you get a warning that says you can't do complete operation with no tool selected, something like that, right? You have to have a tool. Now, it turns out you also have to know what machine tool you're going to use, sort of. And the reason you're going to want to know what machine tool you use is because our cutting force times our velocity over here power equals force times velocity. If you try to do a cut that the fixturing can take, that the tool can take, but that the machine tool doesn't have sufficient power for, what does it sound like? Happens all the time at the mini mills in our shop. So I can tell you exactly what it sounds like. Actually, I have notch hearing loss at the frequency where it starts because I've been around those machines so long. And coincidentally, it's the same frequency my oldest daughter has in her voice when she's whining. Not when she's screaming, unfortunately, but when she's whining about stuff. So she'll whine about something, I'll see the lips move. I cannot hear the words. Like, I want to hear the words, right? Fathers are like wrapped around their daughter's little finger, right? So I want to hear the words. I want to make it better, but I don't know. Anyway, so this is the frequency, by the way. So it's at that frequency. That's what it sounds like when the machine tool doesn't have sufficient power for the parameters that we've selected. So you've got to have some idea what the machine tool is. Then fixturing. Okay. So let's assume that we've got sufficient power for our operation. And let's just look at the mechanics. So visualize the machine. Can I do this? Close your eyes. Right. Right. Close your eyes. Everybody visualizing a machine. Okay. What happens mechanically in the machine as the tool path begins? What are the things that you physically see happen in the machine? Because these are the things that are physically going to happen, and we're going to physically have to program the machine to do. It never does anything unless we tell it to. So what happens at the beginning of our program?
Tool spins.
The tool spins. What happens before the tool spins?
Tool gets inserted.
The tool gets loaded into the spindle, right? So we have to load the tool. My other class, I teach it in Olin 107, the big giant lecture hall there. It's got 2 3-level flowing chalkboards that I can write on. And I really just want to move the chalkboard up right now so I can keep writing without losing all this. Somebody, here, let's take a picture. Picture's worth 1,000 words, right? All right. Don't forget anything's on the board. Okay, every tool path now. Right, so that's the overview. Now let's look at what the mechanics are when it's happening. So load the tool. And I don't mean load the tool into the CNC machine when we're doing the setup. I mean the tool gets loaded into the spindle. So we call it a tool change. I don't know, we'll call it tool 1. Right? So the code for that is actually T1 M06 on our Haas machines. And so T1 just says, hey, tool 1, M06 is the command. You don't need to remember this, but the ones that you see frequently, you will remember, and M06 you can see in every program several times. So it loads the tool in the spindle. Okay, what's the next thing we have to do? So we know at some point we have to have our feed speed depth of cut, right? But what's the next thing that physically happens when we're cutting our part after we load the tool? What's the next thing that physically happens? We loaded our tool. What's next? What has to happen next? We spin the tool. All right, spin tool. Right? And so to spin the tool, so here we had to know what the tool was. To spin the tool, we have to have figured out how much material we're going to remove, what's our appropriate spindle speed and all that stuff for the diameter of the tool. Right? So we have to have known surface speed to do this. All right, so we spin the tool. What's next? Move the tool to the part. All right, so if I do it wrong, so all right, let's say the workpiece looked sort of like this. It was a little bit not quite as wide. But let's say this is my workpiece, right? So I get the tool up here, got the tool change location. I spun it. So it turns out internally in the program, we have to tell the tool how long it is. The software takes care of that stuff for you, but it's one of the things that has to happen in there. There's actually you have to call the tool offset. If you're writing the code manually, that's going to be very important. If it doesn't happen, then wherever you tell the tip of the tool to go in your program, it will put the bottom of the spindle. And it will do it with all of the force it has available to it. Believe you me, I've seen it happen. I've also seen a $10,000 gearbox get replaced when the spindle stops too fast. This is a $600 vise involved too, but once you bought the gearbox, you can throw the vise in. All right, so we spin the tool. We make sure the machine knows how long the tool is, all that stuff. That's all set up stuff. Spin the tool. The tool comes to the workpiece. So we move to the workpiece. Now, do I just start going? Do I go right from the tool change to hog the material? No. All right. So we may or may not want to turn on coolant. And that's really depending on the physics of the operation. Some operations run better without coolant, some run better with coolant, some and also which machine you're using, all that stuff. So we move to a point above the workpiece, somewhere approaching the workpiece, somewhere near the workpiece. What do we call that? And usually we'll move to some X and Y location above where we want to go. Then we'll move down and see if it's a milling operation. Certainly, if you're using any of the post processors that we use here at WPI, it does that. After the first time I wiped out the probe. Before that, it didn't do that. So we move to some X and Y location. We come down in Z. What do we call the height that we come down to? We move to a clearance plane. No, it's the other one, right? We move to a clearance plane. Right, so how do we pick? So this is something we pick. We tell the software where's the clearance plane. How do we pick it? What's our criteria that we're looking for here when moving to our clearance plane?
Getting close but not hitting.
Getting close but not hitting. Right, and so close but hitting would be too close. Right, and so close but not hitting, and why do we want to be as close as possible? We don't want to waste any time when we do the next step, right? It's because this motion is a rapid. So that's a rapid movement. We talked about, I think at the very beginning of the class, we talked about the 3 ways the machine moves, and rapid is the one where it goes as fast as it possibly can, and we don't necessarily control the path, right? So we move the workpiece. It goes to this clearance plane in between steps in the operation also. So after it does a little pocket, it'll come up, it'll move over to another one, it'll do a little pocket. Besides not hitting, so close but not hitting means if you've got really good acceleration and deceleration on your machine tool, you can move really fast and you can stop very quickly. Now, in reality, there's servo motor controlled machines. So in reality, when I tell it to go from here to here, what it does, if it's a rapid move, right, what it does is it goes here, and there's a little bit of feedback because they're feedback controlled. So it'll say, I'm here, oh shit, I passed, back up, come back, right? So it'll do a little bit of this. So too close could be mathematically it shouldn't have touched, but the deceleration was not sufficient to stop it when it got there. It's trying to not hit it. Okay, so you're gonna leave, how much clearance do you need? As we say in the machine shop, clearance is clearance. It needs to not be touching. 50 thousandths is not touching. 5 thousandths is not touching. 5 10,000ths is not touching, but ooh, is it scary. Right, so clearance is clearance. That's that clearance. What else are we worried about with our clearance plane? We're worried about those big honking fixture clamps that we put around the part to hold it in place, right? Sometimes we may want to have that clearance plane be way up high so that we're certain that in between, especially drilling operations, people always crash in a drilling operation. So when I made this face right here, this bottom face, it's got that hole pattern on it. Yeah, so what the machine tool wants to do when you've given it a hole pattern like this to drill, if you drilled it from this side, no big deal, right? You come to a clearance plane, you drill a hole, you come up, you drill a hole, you come up, drill a hole, you come up, drill a hole, you come up. If you're drilling it from this side, you come to a clearance plane, you drill a hole, you come up, drill a hole, you come up, drill a hole, you come up, crash. So if I'm drilling it from this side, I've got to set the clearance plane up here. If I'm drilling it from this side, I can set the clearance plane almost touching the workpiece. Right, so those things to worry about. You've got to have this clearance, and you've got to have this move every tool path, no matter if it's the first one from the tool change or if it's moving from one drilling operation to the next. Every tool path has a move to the start of the operation. That does the operation. And sometimes you'll hear, so it's going to this clearance plane, you'll hear lead in, and then obviously lead out is coming from there. You'll see approach. Delete one of those P's, I think. So different people, different software will call it different things, but you've got to have this move to the workpiece. It'll involve some kind of a clearance plane. In your programming, there's actually like 3 or 4 different clearance planes you can set. When you set up the part, you usually set an overall clearance plane. Then there's an in-operation clearance plane that it picks stuff. There's different things, but this is what this means. And if you don't know what it means, you will crash the machine. Load the tool, spin the tool, move the clearance plane, apply the feed speed depth of cut, right? The next thing is a toolpath that applies the feed speed depth of cut. Now you get to pick how you're doing it. So let's say we wanted to make a pocket that was roughly this shape. We could come in at the center and we could spiral out and then maybe make a contour to finish up the pocket. We could do it like that. What's the problem with coming in at the center? Let's pretend we're laying inside the machine. And here's my cutting tool above me. Now, before it comes down, we want to spin it, right? So it starts spinning, and I won't be able to see the flutes anymore, but they're still there. What's the units for speed again? Surface feet per minute. 100% of the material removal in the cutting happens from the spinning of the spindle, as long as you neglect the part of it that comes from moving X, Y, and Z. But the scale of the two things is such that you almost always neglect the X, Y, Z motion when you're trying to understand how the cutting is happening, the physics of the material removal. What's the surface speed here? When my tool's plunging down. It's 0 if you believe that we neglect X, Y, Z motion. It's whatever the Z feed rate is otherwise, right? If your Z feed rate is going to be something like, I don't know, 9 inches per minute. Something like that. The surface speed that tool wants to make an efficient cut is going to be something like 4,000 feet per minute. Different, not same. So, I mean, we're never going to achieve 4,000, but even if we're at 1,000, still not the same, right? So, no cutting is happening at the center. It's just mushing material out of the way. We could do that. We got thousands of pounds of force and the thrust from the motors. But so we could drill a hole first. So this comes with our plan now. So the plan not only has to know feed speed depth of cut, the bulk feed speed depth of cut, but what steps do we want to do and in which order? So if we drill the hole first, and even if it's a blind pocket, so it doesn't go all the way through, you drill a hole, and maybe the tip of the drill gets close to but not to the bottom surface because you don't want to leave a dimple, right? And then you plunge down inside that hole. At least you're only mushing material around through the very last bit of that cut. And I had a good example I should have brought. When you mush the material around, especially when it's aluminum, you do quickly run out of that power. You actually run out of the power, usually though, after the tool, or right at the about when the tool breaks. I've seen it both ways. My browser lost connection to the camera. That's weird. Yeah. Anyways, the camera we're not using, so it doesn't matter. Okay. So toolpath, and you gotta have a plan for the toolpath. Okay. What do we do after we do our X, Y? Yeah.
Would it be more difficult to take, like, if we're using an end mill, for example, add an angle to the piece?
Not if you're using CAM software. And that's usually one of the options for something like this is you can have it ramp along a pass so it moves sideways. And so the part that's got 0 surface speed is never actually cutting because it's moving sideways and down at the same time. The other thing is spiraling, and we usually helix or spiral into a hole. That's the one I usually choose. I don't know, it just appears in my mind to be more elegant to do a helix than it does to go back and forth. No physics involved, just my interpretation of the beauty of cutting. So you can do that. You can drill a hole first. You can, if it's possible, if you have access, right? So I've got this shape here. This giant pocket has a big opening at this end, right? So I can just plunge down in space and then come in from the side, which is absolutely how we did this. So it was in this orientation, and we came down over here and actually did a spiraling tool path in there. The other thing you want to, so I talk about the surface speed being 0 at the center, because I don't know, because everybody seems to forget. I talk about that, but the other thing is you've got to have some place for the chips to go. So you need chip evacuation. So you need some place for the chips to get out. And so often we'll do a tool path where we come in and we take a little scallop, and a little scallop, and a little scallop, and a little scallop, and a little scallop. So everything behind me had a place for the chips to go. And the reason to do a scallop and not just like a zigzag back and forth has to do with wanting the tool to always be in the same direction, and it loads the tool in one direction, makes the cutting operation itself more stable for the machine. But you got to have chip evacuation. That's one of the primary reasons we use coolant, is to force the chips out of the area that we're cutting in. Move the workpiece, tool path. This tool path is done. Move away. Right. Every tool path is going to have these things. Every step in the way, in order to figure this out, you've got to know what the finished part looks like. You've got to know what the part you started with looks like at every point along the way. And so you're going to have all those steps. You're going to know where's the fixturing, how are you holding it, how much cutting force can you handle, all those things. But that's it. Everything else is about tweaking it to make it go faster, or little incremental improvement kind of things. These are the things that you have to have. I guess move away, stop, spindle, right? Put tool away. So you got to approach, you've got to exit. You got to do the tool path, and when you're doing the tool path, you got to think about what's the surface speed at the center of the tool. Where are the chips going to go? Where is the fixturing? Do I need to set that clearance plane extra high so I can avoid the other things? So to make all of these decisions, to understand all of this, you don't have to have CAM software, and you don't have to be able to write G code, right? All of this. Now, some of it, the CAM software will help you with. There's going to be a default clearance plane that your software is going to pick for you. It's not necessarily the correct one, right? So there's things in there that the CAM software tries to make it so you don't have to worry about it. But, well, whoever presses the start button is responsible for the crash. Even if they try to throw the programmer under the bus. Whoever's pressed the start button is responsible for the crash. Okay, so we've got, what time is it? 9:43. What's my schedule say? I have a schedule. 9:43. Hey, only 10 minutes late. It's pretty good. Considering we had the days. Which I didn't use any of the ones they brought me because the one that I found worked. Should have tried one first. I know none of them would have worked. All right. So, is there anybody that's solo in their group right now? We have multiple representatives from each group. Okay. What I would like is for each group to, we can leave this up here, you can pass it around, however you want to do it, to write out in words how you think you would make this part. So this is just how do you think you would make this part step by step. So at the highest level, you don't have to say cut the stock with a bandsaw, although that hadn't happened. right? So you get your stock material, describe what the stock material looks like. It is 6061 aluminum. You don't have to worry about that, but describe what the stock material looks like, how you would fixture it in the machine, what operations you would do to make what features, okay? So each group get together and decide how to make this part. I'll leave it right here. And you guys can configure in your group. We'll reconvene. It says 10:10. I'll split the difference, do 10:15. We'll reconvene at 10:15. Write out how you would make this part. I don't have a tape measure, but that's 8 inches. So you get scale.
It's like 10 or 11.
Something like that. Oh, yeah, something like that.
These pockets are really deep.
So
They are.
it's impressive shape. So that bit very small.
This corner. So 3/8. Oh, it's the same.
Depends, right? You can't, once you machine out the other piece,
I don't remember. Could have been a quarter inch.
you have some soft job, right? Like, I think before you do that, are there features that you can do the features, but it's still like a simple piece of it?
One side. That's the tool. One side of it. But the other side.
I'm just wondering, can you do that last? Can you do like everything else before you do those two features? And then,
I think
Yeah. No, I'm just gonna put the camera out. Go ahead.
yeah,
You can take it.
you do that as just like a last pass. So this assumes like you just have a precise piece of billet, you put it in that fixture. You have to do searchings from the bottom though. You either, no matter what, there's two operations required. And then if you
Start with the plane. And then
What I'm thinking about how to like is if I had to have a certain straight space, I can use some job. It's possible.
yeah, so I guess what my original assumption was, like, or thought was that if you could do these features early and you're locating features in like
this back.
picture plate, right? Like you know where the cars, you have like, you can like tap the holes in that position on like that piece, and you put that in the ice and you suspend it off that, right?
That's
Yeah.
my thought. But those are probably don't work. Yeah, everyone has to.
And you could like, if these are the size of a nominal fastener, if you have at least two of them and you've located them relative to any position.
So you can start. No, it's like
So okay, what if this is just a flat?
Yeah, I'm gonna take a couple pictures so I can put it up on the screen.
And it's just like a square piece of building, then you do the bottom side first,
the bottom side
right?
first.
And then like the only bottom feature you
You
get.
count. You can fold it down.
Well, I think you can do the bottom first, right? And then you flip it over. I mean, like maybe this is too slow, but then you flip it over and locate it again, and then you set the top stuff.
So you want to fold the piece on another piece and you start. Or the. I mean, we can do the bottom first, that's fine. We can do all of it.
Like you just do.
I think you
just
just do
holes
these.
and you use like a top step, and then you flip it over to do like an overall.
How do you put this on?
You know where you make a fixture plate, okay? You make a plate that has threaded holes or whatever, and then you locate these. You see that also, so you know where these are relative to a feature.
Then you screw them with this, or you can machine.
You also turn the second picture.
Yeah, I mean, I guess that is the hard part, is like you can't do all of this.
Well,
at the same time.
what if,
So timing of the hole will be machined out because the top is gonna be here.
Yeah.
The screw gonna be this low. I need to come in to screw down.
I don't know, follow what you're.
So the screw head is gonna be coming up over this
Yeah.
face.
Oh, no, coming up here.
No. Okay, so I think after you flip it over, you're gonna bolt it, or you're gonna
So you
slice
start
it
out
like
like
down here, so you can basically contour out. Like you'll still have like a rectangle, but you'll have a roll shape.
Yeah, so I guess what I mean is
bolt it down, like here.
maybe what you have to do is maybe you have to do both faces of this part, so you have it what you want, and then you use your facial blade to do the other stuff. Because that makes, I'm just trying to get you to a point where like you can get out to this because once you've done this, you've lost all your other locations, right? You don't have any parallel faces.
Pretty much stand out of that.
Yeah, I think no matter what, that's what you do, right? But somehow you need to turn this area here, I think, like your fixture.
And then I would want to take it as like rectangular. If you want to.
I mean, maybe it makes sense to just go on the top, start your shape the other way. Maybe you do this, then you do you contour out as much of this as you can, hold, etc. Flip, do the finish off that. Okay, so you do that first, then you do what I'm describing, and then you move from the device to the fixture plate to do the like actual external features.
Yeah, that's probably.
Because like also because this is the hardest feature. These are the hardest features in these pockets. Like I guess I don't know. Maybe
No, not really.
you get a small enough edge that you're sticking out. That's like always like exciting to do because you need to have an end mill with a small enough radius to these cuts that also
It's probably use of one piece.
I'm making a slide that's got the whole thing to put up on the screen too.
Okay, that's the picture for you.
on canvas.
I think you look at the back first.
Yeah.
Start with this first off.
So that comes before, obviously.
Starting a rectangular piece of stuff.
Let's do the bottom. We have to. I would just. For the back, the center doesn't matter. Probably.
I guess since you already have the end of it. I guess it doesn't work.
No. I guess you start with a rectangular piece of stock device. We cut it on the bottom and the top piece first. You don't have to swap back to it, so otherwise you never have to go back to that side. So then what you do is you flip it over and then you while it's still just device with the same parallel faces, you just any of the top features as well side.
So pretty much, yeah, first you do the circular side, the flat side. Flatten that out.
Yeah, you get everything to the right depth and features. You can't do anything on the curve. Maybe that same feature unless you use or if you have a middle axis for it.
No, you have to just slow like the step.
Stepwise.
So I just feel like if you do the whole last,
But is that good enough? I thought, I mean, it's actual, like, it depends if that's a cosmetic feature or like an actual needs to be in the writing.
So like that last step back of it. So let's talk about the top piece, right?
So like we get we face it down to depth wise. I guess it's
yeah, so that's what I was saying. The first thing you do.
Okay, so
so you can't see my screen at all. It's light. It's dirty.
So you do where the circle is, the circular side is, you face it down to that surface. And now I need the ridges. The last, I did for the part there. That's good.
Okay, so you want to do
So the next step in the process for this part is powder
So then
coating.
you want this verify.
was powder coated after this was done, and that particular one was a scrap part.
It's like the fakes and stuff, the pumpkining,
Was it because like near the
like the hogging out a ton of material.
Yeah, it's just one of the
Just
parts.
all of
That's
that
tough.
stuff, like,
You do the 3 ridges.
look at the 3 ridges,
Oh,
slice
sure.
ribs, or whatever they're called.
Yes.
It's a structural part for a robot.
There's another hole there.
enough material for it to be light.
Yeah, okay, so we do those things. But I would say then you wanna, then
Those
you
are
wanna,
2 like the bigger hole.
I mean, I assume that what you do is you machine the whole part out on the bottom, and then on the other side you face down to the right depth. That's what you do for those, like the.
Oh, it's also on the bottom, out of the bottom.
Because again, if it's starting as a rectangle,
Yeah.
it's that like way to shape.
Yeah, which part?
Along the outside.
I guess I'm not just.
I don't think you need to, I think you would in fixture plate, you stack it, you cut into it.
No. Oh.
Have you ever seen they make like, you cut full depth on the top, you cut it out.
No,
It's like for chamfer, let's get that out of the way.
Right, is there trying to look
There
back?
is chamfer.
Because that's your like this
And I guess you have to.
doing like this flat surface.
Is that critical? Is the chamfer a machine thing or is that?
Yeah,
I mean, this, it depends on like. What part
Yeah,
right? Like, I mean,
how
yeah,
does
we
it
need
work
to
when
make
you're making a good point?
I meant like, I guess that's what I was talking about, like.
Yeah.
This, like these kind of parts, right, where like they're fastened into the fixture plate, and then like you do the entire depth of the stock. So you always keep it as part of the stock until you want it to stop being part of the stock.
Because I had to get teardrop.
Okay, so I'll note that, you might need to do. You might need to.
Or you just like bolts or something like that.
If the chamfers.
Yeah, so what I made was definitely bolted to a fixture plate for one of the operations.
Okay,
That fixture was held in a vise, so the answer is both yes and no.
right, so like.
But like, for
then I
example,
guess
like that
you're
is,
right
that's
about
adding
drilling
time
holes
and
first,
annoyance
that's
to it, right?
Yeah.
To your machine op. So if you don't, right, if that doesn't matter to the next part. Yeah. In the image it kind of does from the lighting, I don't actually know, like, it looks like there's a lighter strip on the edge. Is there a chamfer on the hard surfaces of this?
There's a chamfer on this edge.
Is that an important feature or
There's
not?
It was on the call out, it was on the spec.
Okay, yep, that makes sense. So then, yeah.
It was definitely an important feature because you wouldn't want that surface to catch on anything in operation. So that was the functional chamfer,
Yep.
not just cut out. Yeah, there's no sharp edges on the part except for the entrances to those pockets. On the top side, maybe not even. Yeah.
Okay.
And they didn't spec a chamfer there because they knew it was going to be impossible to make. This part was designed by somebody that understood machining and did not design features that were difficult to make that were not necessary to the function.
For the inside chamfer, like the reason they couldn't do that is just because the height of the chamfering tool, or is there another reason that would be?
To put a chamfer on
Yeah,
these
I don't actually know
pockets,
what
it was going to be. I'm pretty sure they left it out. There might have been a little broken edge there, but it's difficult just to reach that surface.
Okay, that's what I was thinking. It's already pretty deep into the part.
Yeah.
So.
Yeah, so I'm breaking a piece of the stock in the vice beam. Swap back. Okay, well, it's including your chamfer thing. Speak for contour of the bottom chamfer. You flip it over. Use like parallel faces, right? So you have to actually cut out the whole thing. Cut as much of the interior feature from the top face as possible. So there's height, pocketing, hog up.
Yeah, I would say.
Well, I mean, I have these, you can break it down into more steps, right?
So you have to.
But these are all like I don't work on the flip, and then you have all these tools and stuff, and like you can break it down more.
Okay, so you have to do the half circle.
I have a YouTube video of it.
Because
But
that's another
I
step.
it was ever
Yeah, so
fulfilling
first
the design function of the video.
our other edge to right height.
So you can just observe it sitting there.
To get right.
That's
global.
some sort of.
That was
You want to do this point, you want to do that after.
It's like making sure that's why you have.
Okay, so, is it,
Why don't
maybe
No, just send me a mail.
middle, but, so I guess I don't really understand this, like, this process. I thought you would need to, unless you're doing any other process, you would need to part.
Yeah.
Is it what it is?
But usually they still the middle.
But is that actually like a resolution of that accurate information because it's like, it's like a step of like a fraction of an inch or something.
It's close enough, you can do some finish on them. Send it down, but
Yeah, I mean, I guess maybe I've only ever done parts where we actually literally did use the head, turn it, you can cut it, that's every single thing. Yeah, I know. So I guess saying like if this is better than that, then you can just do it.
it's good enough.
Okay.
Does everybody got a plan for how they want to make the part?
Like so right it there.
Yeah, so like I started bigger content first.
Bigger part, which is like slowing it down. I guess all these imply that you're removing a bunch of material, but then you do need probably like a finishing pass, and then it's like a yeah, then you do the like lighting. And then at this point we move it and put it in our like fixture plate.
No, you can put to the jacket.
Yeah, okay. You do the chamfer on the angle, or well, it's stepwise dispersion.
Still, it's the same thing. So,
Yeah, okay. That actually might be easier. So, okay.
so
Fixture plate.
You guys have a good start on a plan? Everybody got a good start on a plan? We'll get back together. All right. So what's the complicating parts of making this?
Fixturing.
So fixturing is going to be a complicated piece of this particular part. Oh, who wants to see the part in action? Okay. Oh, no audio. I guess I can put the audio back. I don't know if it'll work. All right, who sees the part? Did you see the part?
Yeah.
There's two of them. They're right here. It's if the robot was flipped over so that it could still drive around even though it was upside down. So the drag wheels in the back. So it was to allow the thing to get flipped over in the competition. It also was to protect the spinning weapon from getting something jammed in it from the side. So that was what this part was. Anybody have a guess on how long it took us to make that one you're holding?
Just machine and design everything.
How long it took to machine the part, the physical parts?
3 or 4 hours.
3 or 4 hours. I asked one of the lab machinists the same question this morning. He had the same answer as you. What do you think? How long did it take? How long did it make this part?
Because you're asking by a little longer, like
A little bit longer. Okay.
2 or 3 hours.
2 or 3 hours. What do you guys think? About the same. Yeah, and I think if I looked at it, I would probably guess about the same. 45 minutes. Wow. 3 days to write the program. 45 minutes to make the part, but then we were pumping out the parts one after another. Actually, we made a couple, and then this was a couple years ago. I got a call on Sunday afternoon and said Sunday morning, I guess it was. It said we need some more of those pieces. It was during the filming of the competition, and so we made I think 6 or 7 more on Sunday and shipped them out and had them on Monday morning. Yeah, so I'll talk about the process that I use, but how about somebody? What are the steps that you guys thought to use? I'll start here. Just quickly go through how you're gonna fixture the part and what operations you're gonna do.
Yeah, so obviously we're assuming that we're starting out with like a rectangular piece of stuff.
Right. Yeah, we started with a rectangular piece of billet material.
So you would initially attach it with like the traditional device.
With a device.
Start with like the bottom pockets and the holes.
So this surface first.
Flat surface,
Yep.
yeah. So get those in first, get the holes started, then flip it over, finish the holes so that you can bolt it in. As you sort of mentioned, bolt it into a fixture plate so that you can cut out the teardrop chip without worrying about the device.
Okay. What do you guys in the back think?
So
I should probably pass the microwave for the microphone around, huh?
We thought that like you would fixture it like you would rectangular first, and then
So which side facing up first?
the back side.
This same side facing up. Is that okay?
Say the pockets and whatnot. Then
All right. Hold on just a second. Does any group have a different side facing up first? Okay, so we're all in agreement. When I made the part, I had that side facing up first.
then flip it over and
Flip it over.
profile it so that it's the same like slanted
Yeah.
shape.
So you did this side. You made the holes. You flipped it over, bolted it down onto a fixture plate.
Kept it with the same vise.
Okay, you flipped it over, kept it in the vise.
Yeah. And then I profiled it and have the back hole that has the flat.
Yeah, down here.
No, yeah. Make it so that that part's flat and just have the other side as well. Make sure that the place where you bolt it is flat.
Yeah. Got it.
On both sides. And bolt it and then make the teardrop shape.
Okay, I think I can picture that. Wait. Yes.
What another way to fixture it on the side of the ribs be to use a vise to clamp like the big circle and also use like a dowel or a bolt to clamp or to
So clamp it here.
Yeah.
And put some sort of a bolt through that hole. You could hold the part that way, yeah. Was your plan significantly different?
No, I think we agreed that like doing that back plate first or the same step
Yeah.
and then not like and then fixturing it and then keeping that same fixture the rest of the time would make it a lot easier rather than trying to change dimensions and then like it's only
Yeah.
one thing that you have to change and the machine can do the rest after you film it.
Sure. So I think the simplest way, the way that would take 3 or 4 hours to cut it, would be to do the backside, just like we said. Now, you didn't mention when you went through the details about making this, but we also put the chamfer on
Right.
at that point. And so when we put the chamfer on, it looks like an engraving, right? It's just the shape that was going to be there. and then to flip it over onto a fixture plate. But you have to be able to hold it from underneath with your fixture plate at this point, right?
Right.
So when you make these holes, then you would have to thread those holes to do this. And you could bolt it from the other side with those threaded holes through your fixture plate. And then you can make all of the shapes that you can see from here, you can make from the top. Right? You can do 3-axis motion to make all of that shape from the top. But then you have to take those bolts out. And you have to finish these holes. And you could do that as a manual operation, right? You could hand drill to finish out those holes just to get rid of the threading. You could do that. I would be worried about this one at this end with that technique. But you could do that. And if you did this, I think to make this shape with a combination of surfacing operations and everything would take a couple hours to do the whole setup. I was in a hurry, and I knew that I could get rid of a lot more material if I held it with this side up. And I just cut a profile, right? I did another open pocket here. Then I flipped it over because I didn't have a tool that could reach all the way across. And I had to hold it with something. So then I flipped it over and did the same thing on the other side to get rid of that. We flipped the part back and forth several times. Rather than threading these holes, we held it when it was still square and we made the internal features. Then we could bolt it down onto the fixture plate using these holes. So you can, there's a lot of different ways that you can make any part. But the reason I saved so much time was because I didn't do a surfacing operation to remove all this. I did as much of it as I could with a pocketing operation. The point is, not that I'm smarter than you, although maybe. No. The point is that I spent 3 days figuring out what's the fastest way I can make these parts, because I knew when I got to the moment of needing to make the parts, I was going to want to make it fast. If I just needed to make one part, I would do it. What's the simplest way I can make this part? And the simplest way is with a couple of setups and some manual operations afterwards. Right. Okay. That was good. Back at my schedule. Okay. Let's do a quick screen up. Projector mute. No, I don't want to turn it off. Cancel. When they started putting these podium things in the classrooms here, it was pretty cool if you got assigned to a classroom that had one. You felt pretty special. You felt pretty high tech, because not all the classrooms did. The problem is, as they've rolled them out across the campus, each one is unique. No two of them have exactly the same controls as far as I can tell. So it's easy to press the wrong buttons. All right, so as you're working on doing your programming for your class project, for the group project, think through these things as you're doing it, and I think it'll be super helpful. And just remember that every operation has to have these different steps, and everything else is just frivolous. Frivolous is a cool word. All right. So, what group project communications still need to happen? What information does your group need from another group still?
Maybe not like specific, but like the people just started sharing whatever they have, start trying to put together.
Okay. I wonder if the easiest way to do that is well, there's plenty of easy ways to do that. The easiest way for me to initiate is in Canvas. So if we go in here, this is this class, right? And so if we go to discussion forum, did everybody see this, by the way? Your feedback from your group presentations. Did everybody see it? Did anybody see it? So if you go to Canvas, you go to discussions. So your feedback for your group for the group discussion, I assume that we can make it bigger. And so we stripped out the names of the people that made the comments and the questions, but gave you the comments and the questions. And the one for your group. Did you post the right stuff? So it's supposed to be how people felt about you in your presentation. Yep, this is the wrong quiz. It needs to be the quiz from last Thursday. Right, it's so that they can know what everybody thought about their presentation. So we'll update that. We'll fix that. Is that all of them or just that one? Yep. Yeah, so you need to download the correct quiz. You got it? We can meet in my office right after this. Okay, but that's the idea at any rate. That's where the information will be, and you can look at everybody's feedback from your presentation. Okay, but let's make a discussion forum thread. New discussion. All right, so each group can create a thread here with your design, and then if somebody has questions about it, they can reply to the thread. So so we can keep each individual one separate. That way everybody can benefit from the answers. So we'll do that. Is there anything else though specifically that anybody needs? I believe the bearings arrived today. They were ordered on Friday for sure. I get an order confirmation.
So moving forward, maybe you actually buy stock specifically for us and people who are going to make parts, or do you just look at this I think that would aid a little bit.
You should tell me what stock you need.
Okay. We just like put it in the PO kind of thing, or just like
We should have a conversation.
okay.
We can do that right after class. Yeah, so I think we already have the stock that your group needs. What stock do you want to cut your part out of? Okay. All right. Well, let's talk. If you need something, we need to order it. But I did get bearings because the ones that I thought we had got cleaned up last term, and I got little spin-on threaded fasteners to use, thumb screw things to use to hold it together, so we don't have to make that part. So I ordered those. Anything else that the groups need individually or from each other? Yeah.
So I was wondering if I could get like CAD models for everybody just to like make it full build. So I'm gonna put one of each, so one bearing and I left one empty, so you can see what it looks like.
Okay.
And this is from the other group that's gonna give me a class and that's gonna go there as well. I'll only put like one of each just to see what's in the
Okay.
Yeah.
So if you have your parts designed, right? Does everybody have a design for their part? Like a SolidWorks or Fusion or AutoCAD? I don't really care what software you used. Does everybody have a design? Okay, so if you can put your design in this discussion forum thread, then and then you're gonna take on putting it all together. Okay, perfect. Bonus action from a group here. Just to make sure. I guess you are making the part that everything fits into, right? Yeah, it kind of makes sense. All right. So we'll do that. Any other group questions? We're ready for Thursday. We should have a presentation of your current status, parts that you've made, problems that you're having. If you're having problems, what help do you need to get past those problems? Don't wait. If you're having a problem today, don't wait till Thursday to ask for the help, right? Let's get some help sooner. But each group should be ready to present where they are. We have like 10 minutes per group. So you should also be talking about the process that you're using and the things that you had to learn in order to do this process. So the things that I find that the people that are best at teaching something like this are the people that are just learning it, because they realize what was hard for them to understand and to get. Whereas when I talk about stuff like this, I've been doing it for 20, 30 years, I forget the things that I was hung up on at the beginning. So it's hard for me to remember those things. So bring those things out and as discussion topics. If there's something that you want help from the rest of the class, make sure you're ready to present that to us as we do this. Okay. All right. So I have one more little group activity to do, and we'll report back from that, and then we'll probably end a little bit early. So the people that I said, let's meet after class, we can do that even before the time is over. One of the things that I do to help myself stay focused and to stay on the track of the thing that I'm doing today. And so this is life lesson for everybody, not so much manufacturing lesson, but it'll help you. One of the things I do is you want to set the tone correctly. I read this book called Zen Habits, and the author of the book, it was about being anti-time management, but that doesn't in the sense of overgeneralization. Anyway, but he said one of the things that who's ever written a haiku? Who knows what the form of a haiku is? So it's 17 syllables. It's 5 syllables, 7 syllables, and then 5 syllables. Now, traditionally, a haiku should be written in Japanese. Does anybody here speak Japanese? All right, so we won't be doing that. Traditionally, a haiku should be written in Japanese, and it should be about nature. Since this is America, we're going to throw the rules out. It does not have to be about nature. In fact, it has to be about toolpaths and the steps to making a toolpath. And the reason I like to talk about this guy, Leo Babauta, that wrote the Zen Habits book, is because he said that anyone can write a haiku on any topic. In fact, I've used an AI to write a haiku on machining. Turns out it sucked. To write the best haiku on a subject, you need to think of what are the most important 17 syllables about that subject. And if you can think of the most important 17 syllables about that subject and put them together, now you've written a really good haiku. And so I use this as a tool in the mornings. I think about what's the big thing that I'm going to struggle with today? What's the thing that I'm having trouble with today? And I try to write a haiku that's going to put that in the front of my mind and also make it seem like it's easy for me. But what I'd like you to do to think back on what we talked about today and how it impacts you in your project and you as a better engineer is to think of a haiku that describes the required steps for creating a toolpath. Right, so you could throw it together, 17 syllables. You could all pick them. Or you could, as your group, so do this in your group, right? Let's take 6.5 minutes, and then everybody will report back their haiku, and then we'll be done for today. Me too. I'm gonna do one too. We do need a poet laureate for the campus. That's you? All right, you guys are ready? You ready? You ready? You ready? You ready? This is really easy to do poetry with people singing at you. How come they're making you write it? You were sleeping half the time. That's right under the bus right there. The guy who was asleep half the time is writing the haiku. Well, make it about dreaming. It came to me in a dream. It came to me in a dream. That's 7 right there. It came to me in a dream. All right. While you're thinking about yours, I'll share mine. I did already, didn't I? Refresh. So, not my first rodeo. I have written a haiku on this topic before. My favorite haiku is kind of on this topic. Feed speed, depth of cut, guessing, not recommended, carbide, explosion. But today I have each step is the same. Art, part, toolpath, and fixture. It's really simple. You ready, Poet Laureate? Wait. Get you on mic. Get you all mic'd up.
All right, we got sick. Loading the tool now. Spin up. Approach the workpiece. How fast and how much?
You ready? Ooh. Who's the quarterback that always throws them like that?
Adjust the lathe chuck. Get values from other groups. G-code will take that.
Okay, that's fair. He's still writing away.
All right.
It's remarkable that he hasn't got a haiku yet.
Move to clearance plane. Set feed speed and depth of cut. Make sure you don't crash.
Fair. All right,
I got it. Toolpath haiku suck. It came to me in a dream. Just don't crash the tool.
Spiteful, I like it. So I was only picking on you a little bit for dozing. I figure if the students in the classroom are sleeping, it's my fault, not theirs, right? I wasn't engaging enough to keep them awake. My favorite, I have two favorite sleeping student stories. Anybody ever have a class with Chris Brown, Professor Brown? Did he have the monkey? He used to have this screaming monkey. It was like a slingshot thing. And so he would bring it with him into the lecture hall. And if a student was nodding off, he would encourage them to be awake by picking it up and shooting the screaming monkey at them. So you wake up in the middle of class with a screaming monkey flying at your face. Funny for everybody else, not so much for the person that receives it, I think. So my second favorite sleeping student story was back when we did course evaluations on paper. So he had his head down on his arms, sound asleep. Everybody's talking. We're having a discussion, talking about that I'm handing out the forms. No motion at all. He was asleep. So I lifted his elbow and slid the form under and put his elbow back down. And he didn't wake up still. The whole class was laughing riotously, like a riot. Anyway, that's my top three. Number one was in AK. What's the really big lecture hall in AK? The 116. That's the one. AK 116. I was a sophomore probably. It was macroeconomics because you have to do those social science classes to get your ME degree. So sitting in there in that class, and I fell asleep, like the kid with the elbow. And then I woke up in the middle of some double E class. Everybody, I was in the middle of the row. People had to get up and walk around me to exit. Everybody got up, walked around me, left me sleeping there. The other class came in, left me sleeping there. The professor just started and went through the class. Since he didn't bother to wake me up before starting his class, when I woke up, I got up and left the room. So it happens. All right. Who was coming with you? You had something you were coming. Oh, stock. We're talking about stock. Do you guys need to come talk about stock too? We can do that right now. Okay. And we need to talk about what quiz to upload the results of.
So we talked with Rio on Friday.
Yeah.
And,
Let me just turn this off.
yeah, no worries.